Uh, Everyone can hear me? Good morning, everyone. My name is Bruno Boaretto. I'm doing my postdoc at the Institute of Science and Technology at the Federal University of São Paulo, under the supervision of Professor Albert Macau. And today, I would like to talk about one of our recent results, a very simple result, a very honest result, which calls phase synchronization of connected neurons under the effect of Poissonian inputs. So imagine that we have a huge network with thousands, millions, billions of network. But we don't have access to all of those neurons. We have access only to a small region of this huge network. Our first of course, we know that there is interactions among neurons inside of this area, but also these neurons are interacting with the outer media. So how can we simulate the activity that comes from neurons that we don't have access? Of course, noise is a good answer for this, but in this project, we tried something different. We applied a train of Poissonian spikes. And with this in mind, what we want to know is how does phase synchronization emerge in a network under the effect of this type of activity, with this bombarding of a train of Poissonian spikes in our network, all right? That's our question. So in this project, we use the well-known Hutchinson model. Fernando told us a little bit about it. So the neuron model simulates the variations in the membrane potentials as a function of 3 ionic currents plus an external current here. This external current is the current which gives life to our neurons. So it's the current which produces excitation activity in the neuron. If you study how the external current as a constant parameter, and even more, if you study how this parameter changes the dynamics, which means that we will study the I as a bifurcation parameter here. For lower values of I, the neuron, the system presents a stable fixed point. If we increase the current, the system passes through a subcritical Hall bifurcation, giving rise to a stable limit cycle, which is associated with the spiking activity, with the oscillatory activity of the neuron. If you keep increasing the current, the external current, there is a shrink in the limit cycle due to another Hall bifurcation, but in this case here, we have a supercritical Hall bifurcation. So if you keep increasing I, we achieve another fixed point here. So there is a range of constant current that the neuron presents spiking activity, which means that greater is the current here, greater is the current, smallest is the amplitude of oscillation, and greater is the frequency. This is what happens when you apply a constant current to excitate the neuronal model. But as I mentioned in the beginning of this presentation, we don't want to apply a constant current. What we want to do is to excitate our neurons with a train of Poissonian spikes in a way to think about, to simulate the spontaneous activity which comes from other regions that we don't have access. With this, our current is not constant anymore. So it depends on a G factor, which controls the strength of this external current. This second term here is to produce an excitatory synapse, which means that it's a positive value, so we are increasing the membrane potential of the neuron. And the S value here takes into account the time when an external spike arrives at our neuron. So here we have an illustration of how this happens. The gray bars here represent the Poissonian events, and the red line is the increment on S, is this sum over events. So in this sense, what we are doing, we're basically giving small random kicks to excitate our neuron. This is what we are doing here. So I will show a few examples of a comparison between the external current, which is our input, with the membrane potential, the evolution of the membrane potential, which is our output. And each column presents a different rate of Poissonian events. So in the first column, we have 0.01 spikes per millisecond. Of course, we produce these artificially, so we can control the external rate of Poissonian events. Here we have 0.10 spikes per millisecond, and here 1 spikes per millisecond. It's an average, of course. And you observe that greater is the rate of Poisson events we are able to produce spiking activity, electrical activity. Greater is the rate, more spikes we will have. So this is how we can produce, in fact, this is a way to produce irregular spiking activity in the neurons. And this is much more realistic than the periodic behavior produced by a constant current. If you decrease, for an example, if you decrease the external conductance, we lost the spiking activity. We have only a little bit of noise, but we don't have any spiking event. All right? So now I would like to present to you the coupling current. So to study the collective behavior of 100 randomly collected neurons, each neuron receives its own equation. So we have 100 of these equations here, and its own ionic currents. But we are applying for each neuron a distinct external conductance, external current. So each neuron is excitated with its own train of Poissonian events. And the coupling current here takes into account the activity of the other neurons of the network. All right, so the coupling current is characterized by a chemical synapse, a chemical excitatory synapse. Fernando told us a little bit about it. So we have a coupling parameter, epsilon, which controls the strength of the interactions among neurons. The second term, again, is to ensure that this coupling current is positive, so it's an excitatory coupling. We are increasing the memory potential of the neuron. Aij here is the element of the connection matrix, so it tells us about the connection of the neurons, about the topology of the network here, which in case is a random topology. And R is a dynamical variable which represents the kinetic function of the neurotransmitters. We are using this because we are talking about a chemical synapse. So it's not an electrical synapse, all right? And of course, since we talk about phase synchronization, we need to quantify it. In this scenario, we use the Kuramoto order parameter, which quantifies phase synchronization. When R, the modulus of the Kuramoto order parameter, is close to 1, we have synchronization. When it is close to 0, we have desynchronization. If you want to know more about how can we measure phase synchronization to associate the phase synchronization to the memory potential of the neuron, let me know. We can discuss this in another opportunity, all right? So, but in sense, we are using R to evaluate phase synchronization. Now we can go for the results. I think, how much time do we have? Sorry? 8 minutes. 8 minutes, great. So, all right, so considering the same external conductance, G, and external rate of Poissonian events for all neurons, each neuron receives its own external Poissonian train of spikes. So we are excitating each neuron in a different way. For simplicity, we have fixed the external rate of Poissonian spikes in 1 spikes per millisecond. From now, we have only 2 parameters to study, the 2 free parameters to study about synchronization: the coupling parameter and the external conductance parameter, epsilon and G. All right? Here we have an example of how the raster plot. So each dot here corresponds to the spiking activity of a neuron. We are evolving the time on the horizontal scale here. Each column represents a value of the coupling, and each row represents a value of G, which is the external conductance. Looking here, in the first panel, we have an incoherent behavior. As we increase the coupling, we can observe a few vertical structures here, which are associated to the phase, a partial phase synchronized state. As we increase, we achieve a phase synchronized state. So increasing the coupling, of course, we are increasing the interactions between the neurons, and we are able to achieve phase synchronization. If we increase the G factor, we observe here that for the same value of coupling, we don't have synchronization anymore here in this situation. Of course, we are increasing the incoherence in our network, and this makes the system hard to synchronize. If we keep increasing the external current, we observe here that the interplay between the external excitation plus the coupling current, we are saturating the electrical activity, so the action potential the memory potential of the neuron do not reach an action potential. So it's like, in this situation, we are saturating the neuronal activity. A more general framework can be observed in this surface here. So we have the Kuramoto order parameter here on the left side as a function of epsilon and G. The blue region represents the lack of synchronization, which means that this is incoherent behavior. And the red the red region represents the synchronized state, when the network presents a relevant behavior of synchronization. Of course, if we increase the coupling, we have a transition from non-synchronized to the synchronized state. This is completely expected. And as we increase the external current, we are increasing the strength of the external Poissonian events, which are stochastic, which means that we are increasing the critical coupling, which means that increasing the external stimulation, which is necessary to produce neuronal activity in our network, we are making the system more hard to synchronize. Here on the left side, we made a comparison between the external factor, the average of the whole network, minus the coupling factor. And we observe that when the coupling overcomes the external external current, we have a relevant phase synchronization behavior. All right? So as I mentioned in the beginning of this presentation, this is a very simple result, but it's an honest result. No, it's the same rate of... Pardon? Not is the same noise. Because the coupling factor is very high in this situation. Pardon?
Synchronized dynamics is not absorbing state, is it?
No.
How can this be possible?
Well, I think in this situation, the coupling is so high that the coupling factor overcomes the coupling current is much higher than the external current. Yeah, but in this case, the noise is irrelevant in comparison with the coupling activity. The noise in this situation when we have...
R has a distribution, right?
Yeah.
So you're saying that the R is 0?
I couldn't understand. All right, thank you. I'm sorry. So, yeah, I will proceed. Another relevant question that we can study in our network, since we are applying the external stimulation to all of those neurons, we have a question of what's happening if you apply the noise, the external current, only in a fraction of the network, and we do this in the only half of the network. So here, the colored dots represents the neurons that are receiving the external conductance. This produces incoherence among neurons, electrical activity here, and neurons that are unstimulated due to the external current. In this situation, since they only feel the coupling current, they are able to synchronize. This is very interesting because the same current which produces electrical activity and produces incoherency in this side of the network is able to induce spiking activity in the other side of the network, producing synchronization. And again, as we increase the coupling, we produce synchronization behavior, partial synchronization behavior. Another important feature that we can observe of these results is if we observe, all right, I'm almost finishing. If we observe here, as we increase in the first column for a fixed coupling value, if we increase the external conductance, the G factor, there is a lack of activity on the non-stimulated part of the network. So we are increasing the stimulation, the strength of the stimulation, but the unperturbed fraction of the network is decreasing the activity. And this doesn't make sense at all, and we start to look at what is happening here. So we investigate how the information is transmitted inside of our network. So the postsynaptic neuron receives information from the presynaptic neuron by this variable R. If you look at the presynaptic potential and the presynaptic variable R, we observe that greater is the external conductance, smallest is the amplitude of oscillation of the spike in activity, and in consequence, we have a small, a minimization of the transference of information in the network. So greater is the external current. Remember that the neuron, if we excitate the neuron too much, there is the supercritical bifurcation for greater values of the current. And we are shrink the limit cycle. So increasing the external conductance, we produce this effect that we call the minimization of the coupling effect. So we are dealing with two distinct effects. One is increasing the current. We are increasing the incoherence in the network. But also, we are decreasing the information propagation because the amplitude of the spike oscillation is decreasing. I'm going to the conclusion, all right? 1 minute, sorry. So phase synchronization occurs when the coupling current exceeds the external current, and increase in external conductance disrupts the synchronization through incoherence and minimization effects. The incoherence induced by the external current is pretty much obvious, but the minimization effect is a not so obvious effect. It's particular of the hub bifurcation for greater values of the current. And synchronization can be induced in the non-simulated fraction, while the simulated fraction remains incoherent. If you increase the coupling, we lose the phase synchronization of the entire network in this case, because the coupling is so high in comparison with the external activity, then we are able to, it's not a complete phase synchronized state, it's close to it, it's approximate to one, but it's not, but it's a relevant scenario of synchronization. We have published this result on chaos last year, so I will skip this. Thank you very much.
Thank you, Bruno. We have time for 1 or 2 questions.
So to what I understand, this effect has nothing to do with noise, right? It's just you pump so much the coupling strength, the deterministic scenario synchronizes, then persists over the noise driven.
Yeah, yeah, that's true. That's true. The external current is necessary to produce electrical activity. Otherwise, the network will not fire.
No, I know, but you average out by central limits, you get the current, then you synchronize deterministically, and then there's not destruction.
I couldn't listen, sorry. All right.
Okay, so let's thank Bruno again.
Thank you
We
very much.
can talk to him later. So we have the